Swayam Prabha. Digital India. Educated India.
We will take up some sample models and scenarios and try to perform sensitivity analysis and policy analysis, and I will walk through on how I end up doing the sensitivity analysis, and you can adopt it and further improve it to ensure that we are able to do these things in a proper manner. Let us take first example is infectious diseases dynamics. It builds on whatever model we did, the debugged disease model that we had yesterday. Now, we like to check the sensitivity of the infectious diseases model to say 50% increase in recovery time or 50% increase in contact rate on the initial number of infected people. Instead of 1, it can be 10 or 100. We want to see what happens to the dynamics, and we need to have a base case against which we want to compare the same. So, let me just quickly go over how we can do sensitivity analysis. First let me open. So, this is our model. We have a lot of things happening. So, first I am just going to save as into a new model. So, first we have to check whether our model is saved it as open infectious diseases model, which is saved. When if you actually go to the control panel, data sets, there will be lot of data sets you might have used in the previous cases. It is best to get rid of all of that, so that we have only the base case. So, first is to write here the base case, simulate it and keep it ready. So, that is a base case against which we are going to compare. So, now to do sensitivity analysis, and since all these are parameter changes, we can actually do it without trying to using what is called as the sim setup, without trying to open and save all the settings. So, what we are going to do is I am going to just click this sim setup. So, first case we are going to do is doubling the recovery time, right. So, let us just call it ID recovery time. Now, instead of, so recovery time originally was 0.35 weeks, we are going to double it, so it is going to be 0.7, right. So, let us just call it 0.7 RMS hyphen, and just some names, right. Then you click recovery time. So, as soon as you click the recovery time, when I click sim, then I got this, I changed the title. Once you click recovery time, it will show 0.35, we changed it to 0.7, right, and then click enter. Then when you click simulate, it had already simulated with this one setting, that is. So, now if you actually open recovery time, you will find that it is still 0.35, meaning 0.7 was only used for that simulation run, but you did not change your fundamental base model, which is quite useful because the sensitivity analysis, then if you end up changing many things, then it you will not know what combinations you are actually comparing with after some point, right. So, this is the only change that has occurred. Now, to actually see the results, if you click infected population and click graph, now you can see both the graphs, base case as well as this IDR T04 is what I given, recovery time 0.7. So, it look like for 50% increase or not 50, double the increase, right, from 0.35 to 0.7, it actually increased about say 5,500 to 7,000 would be what, about 25% increase in the infected population. Okay. We will do more. So, even if you did not see it the previous one, we can see it now. Just check it. Okay. So, actually it is not double the, we ran double the recovery time, actually the scenario given is 50% increase in recovery time. So, recovery time is 2.5 days, 50% increase would be how much? 1.25, so 3.75 days. So, 3.75 by 7 would be 0.5, 0.525. So, that is the setting that we should have simulated. So, let us just do that. So, again 50% increase. So, I am going to click sim setup, RT say 55, click recovery time, instead of 0.35 write 0.52, what was it, 525. So, this is 50% increase in the time, in the recovery time. Then I click enter and then I have to click this play button. I click infected population. So, this was doubling the recovery time, we just want 50% increase, so I am just removed that graph. So, 50% increase in the recovery time caused us to peak at much higher. So, recovery time is longer, that means people are taking more time to get, being infected, right, and that is adversely affecting how many new people are getting infected, that is infected persons, that increases about 10%, 5,500 to 6,500, so 20%. Okay. Now, let us do 50% increase in contact rate. The current contact rate is 20, 50% increase means it should be become 30. So, let us just sim setup, the contact rate 30, then contact rate, so 20 I change it to 30. Remember, when I change this, why? What is the recovery time we are using? Recovery time is still 0.35. So, in sensitivity analysis we change only one parameter at a time and this helps us avoid other errors. I click play, infected population, I plot it, let me again remove this ID 07. So, compared to the base case, when the contact rate increases, also we are getting similar peak, but much earlier. So, if contact rate increase 50% or the recovery rate increase 50%, the total infected is the same. That is interesting, that is one. 2, in this case more contact rate happens, more people are getting infected earlier. So, the peak shifts by a few days here, which can have impact on our policy in the sense of how much you want to have beds and things like that. So, this is how sensitivity we do and say how much, then we compare how much the reduction in days is about 2 to 2.5 days has reduced and peak has increased by 25%. For 50% increase in these changes, it results 25% these changes, is how we record it. What is the next one? Initial number of infected people are 10 and 100. So, let us see what happens to that. But infected people, if you look at the function, it is actually written as a variable inside. If it is inside that, then we can't change it. When we do sim the sim, it does not allow us to change the initial value of stock. To make it change, we need to introduce a new variable. Let us call it initial infected. Creating initial infected, I am connecting an arrow connecting initial infected to initial population. Click equation and make the initial value as initial infected. Click OK. Go to the equation, keep this as 1. So, with this as 1 is already the base case we have, right. So, now we can again synth the sim IR initial 10. If you change initial infected to 10, let us run it and let us do initial infected to 100. I just ran 2 runs with different values of initial infected. If you look at the infected population, you get all sorts of interesting graphs. This spot which is the base case, which is this purple line. So, when initial 10 from the base case, the initial was 10, the peak actually shifted. So, as more initial people were there, the peak is now occurring earlier because now the probability of meeting infected person is much higher. So, more people get infected early on. So, peak just shifts left. When initial is 100, it moves left even more. Okay, but the maximum continues to remain the same. It does not change. So, look at recovering population. You can observe that whatever the value you had put, the number of people who recovered is also the same 1000, which does not change. Eventually, everybody gets infected because it is a very basic model, and the susceptibility followed 0. The only changes are the trajectories that has happened compared to the base case, which is in purple here. So, there are some scenarios which delayed the recovery. Versus there are some scenarios which resulted in more people getting recovered much earlier, that is, it is speaking much more. As expected, when you double the recovery time, it took longer to people to recover, right. For all other cases, there are more people already infected, so they will recover faster, I mean in the same amount of time. So, only that is why we are getting different rates. So, this is an example how we can do basic sensitivity analysis using SIM setup, where we are all using Vensim student edition. There is a Vensim Pro edition which allows you to automate it to some extent, where you can give the range of these parameters. It will do all the runs for you and give it. Of course, you have to pay for it. So, I am not showing that. So, there will be an additional set of icons for doing automated sensitivity analysis. This is the manual version, but the logic is to understand how to do it. Automation comes later. Okay. Now, we have all these settings. Now, let us go back to the model. Let us do policy analysis on the same model. Analyze the impact of following policies with the base case. Policy on recovered population does not pose any threat of spreading infected disease as they are quarantined. Once they recover, they leave the place or something, or they got immune so much that they are not spreading disease anymore. Once you got the disease, there is so much say antibiotics in you that you are not able to, you are not spreading the disease. That is a policy. Policy 2's fatality ratio could have been reduced 15% if 100% of population are given antibiotics coverage upfront in anticipation. Currently, the fatality ratio is 90%. So, recall the question. What it says is all the people who are given antibiotic injection, major driver happened, then the fatality ratio will come to 15%. So, when these two policies we want to implement, or policy 3 is combined policy 1 and 2, meaning recovered population is still quarantined and we are doing antibiotics coverage, we are incurring double the cost, so this thing happen. But what will be the dynamics? Will less people get infected? Will it take much longer or shorter? Will the peak be taller or shorter? So, these are questions we want to understand, and based on these policies recommend which is the best one so that people can actually implement it in the field. So, let us go back to our model. First one says that recovered population does not pose any threat as they are quarantined. So, how do we change the model to reflect that? So, now it is said that the recovering population does not affect new people getting infected, right. So, this link should disappear, that is policy 1. Second one was this fatality ratio. It is said that if we do 15%, 100% of people get antibiotics, then fatality ratio goes from current 0.9, 90% to 15%. 0.15. So, this is a parameter change, quite easy, we can do it, but this is a structural change we want to enable, right. So, to do that, let us just create a new variable called policy of quarantined recover. I am going to have a big name, policy of quarantined recovering population. Let us just link it. Now we are just looking at the model. So, infected population, the total population is infected plus recovering plus susceptible. So, I am just going to move this guys here. So, now recovering population, I am going to multiply by the policy of quarantined recovering population. This policy, let us set it to 0 with a comment, and 0 indicates people are quarantined, 1 indicates people are not quarantined, I mean recovered people. So, I am just introducing a new variable there. So, 0 indicates they are being quarantined. So, that means the policy is in effect when it is 0. It is up to us to define whether policy is on or off and what it is to be. So, I am just defining it that way. So, this helps us understand what is a better modeling practice. Now, I can again use a sim setup tool to set the policies. Let us do sim setup and let us call it ID policy 1. Policy of quarantine, instead of 0, let us just make it. Now, 0 means it's already quarantined, right? Right. Let me escape it, stop it. What is the base case we want? We want the base case to be 1 indicates recovered people are not quarantined. So, let us just call that as the base case. Again, as you can observe, we are using the comment box to do the documentation, so it becomes easier for us to figure out what is happening. Now, let us do the sim policy of quarantine. So, if I put 0, that means people are being quarantined, policy 1 happens. Let us play it. Now, for policy 2, let us send the sim, and fatality ratio goes to 15%. So, I am changing fatality ratio to 0.15, clicking enter and running it. And policy 3 is people are quarantined, that is becomes 0, and fatality ratio is 0.15. So, both the changes has occurred. I am going to simulate it. I have 3 different runs, 3 different policies are evaluated. Go to the infected population. All our sensitivity analysis runs are there. I am going to just comment it all out so that we can compare what we actually want. This is the changes we see if we have the base case, which is right here. Now, let us do one policy at a time. Policy 1 actually had no impact. Even if I removed the recovered population, it did not have any impact, right? It did not have any impact, it is almost the same. Policy 2, it reduced the peak infected, because that means putting antibiotics is much more effective. When it did policy 3, when all are there again, there does not need to be any impact. That is quite interesting. Did we get the policies right? We get the policy equations right. Policy of quarantine, initially it is 1. Let me just simulate the base case again. Is policy 3. We would expect policy 3 to be similar to policy 1, right? At least should be similar, but it didn't. Let me just let us again check policy 3. Let me call it B. Now, since I am not happy with sim, what I am going to do is I am going to hard change it here. So, people are quarantined and fatality ratio is 0.15. I am going to hard change in this model so that I can run it. It's so irritating. Yep. Let's do base case and policy. Policy 3, yeah. Doing both seems to have an adverse effect, which is quite counterintuitive result that we are getting. We ensured fatality is small and we quarantine people. That means once they go into recovered, then they are not influencing. If fatality is high, then more people go into diseased stock, right? And diseased stock does not affect our population. We know that. Disease stock is not affecting our the number of people getting infected, but when they go into recovered mode, then and we are removing them from that, still they should have the similar impact. But interesting, it is showing this one. Let us try say recovering population graph. Okay, now we are getting some very interesting results. Base case is here in policy 3, because of policy 3, 3B is the same. More people are recovering, of course, because we gave them the injection, I guess, the antibiotics. Policy 2 also more people are recovering, which is again because of antibiotics effort. In policy 1, the number of people compared to the baseline. Policy 1 just mimics the same baseline case, the same number of people that are recovering. So, it is quite counterintuitive result that we are able to get even in such a simple model, that the number of people who are just providing them with the antibiotics, there is a subtle change here if you observe with policy. I am going to remove base case. Between policy 2 and policy 3, there is a subtle difference. So, including or excluding the recovered population, affecting them did not matter. Antibiotics had a much better effect. So, doing antibiotics and quarantining people did not have much effect. That is one of the very interesting thing that comes out with this model. So, we have done this housing stock dynamics. We can also check sensitivity of model to say, for example, one parameter, time to build houses 6 to 5 months, or time to build houses increases from 6 months to 7 months. And we can analyze impact of one new policy also, saying due to change in FSA rules, authorities are considering replacing every demolished house with 1.25 new houses from month 20 onwards to meet the new demand. If you look at the model, the number of houses, desired number of houses increases 50,000 units in month 20. So, along with it there is a policy also being considered. So, why don't you work on this?